Hello and welcome. We're going to study today is double integration. Okay, so double integration is kind of integration that's in two dimensions. That's in two dimensions of independent variables. Okay, so what do we mean by that? So let's go back to what does single mean? So single is the standard integral we've all known. Integral from a to b of f of x dx, and it's approximately equal to the sum I equals 1 to n of f of x of I times delta x. All right, so the idea here is you have some function. This is the standard definition we all know and love. It goes from a to b on the x-axis. We partition up the space, and what we do is we want to pick some representative value. That's x1. There's another representative value there. We want to find the y values, or the f values there, fi, at each one of these intervals. We add them up, and we multiply by this delta x, which is the width of the little partitions we made. And that gives us some idea of the area under the curve, or it can be, in some instances, the average value of the function in some interval from a to b. All right, so how do we do it for double? Well, it's very similar. The idea now is we have a double integral, which I'll say from a to b. Actually, hold on. We're going to do a double integral over some rectangle. We'll start with rectangles for a while. X comma y. We have a 2D function now. dA. All right, so what do we mean here? We mean that now these are areas. So here, this right here, delta x is the length. All right, so these areas. Now again, the idea here is that that is going to be approximately equal to a double sum f of x of I, y of j, where I now is summed over I equals 1 to n for the x variables, and j is equal to 1 to n. J is equal to 1 over all the way to n, and then we have a dA, which is these tiny areas. Now, a double integral then is basically the same thing as a single integral in the sense that you're at the end of the day, we're just adding up a bunch of representative values of f of x and weighting them. So these are the weights, and these are the representative values. Representative f values. So let's talk about what this rectangle is. So again, we're talking about an area of xy space. So that's the x variable. We'll call that the y right here. And that's our r, our rectangle. So this can go, so again, when we write this integral down, we write two integration symbols stacked together. We put the r underneath it to indicate that it's a double integral over this area, which we call r. And we multiply by this dA, this little tiny area differential, which represents a tiny little box of area. So we can call that right there, and that will be actually, we'll call it delta A, because it's a finite area. And we can tile this whole entire rectangle with a bunch of delta A's. And of course, F is going to be some surface that sits above it, if it does sit above it, that is. So, like that. All right, so, and then the representative F values, of course, if we're going to partition now this entire rectangle, we're going to partition it into a bunch of little patches, just like that. So our delta A is just one of our patches, and we're going to have quite a few of them. So we'll just write them all out like that. So the delta A is actually going to be delta X, and there's also going to be a delta Y, the little length on that side. So we can think of delta A as actually being a product of delta X times delta Y, right? It's going to be the area resulting from a partition of the x-axis and the partition of the y-axis. All right, so that's all nice in theory. And again, it's the same idea. We're going to add up a bunch of things. So let's talk about an example. Okay. So how do we, but before we start with the example, actually I got to do one more thing. Is how do we add these up? Now, in any principle, we can add them up in any order we want, right? Because again, at the end of the day, if I have two variables, call it u plus v, right? That's the same thing as v plus u, right? So whatever order I want to add these up in is totally fine. That's the commutative law of addition. But certainly, we want to have some organized way of adding up these things. So one is we want to think of it, I like to think of it as hay farming. All right, and that's the notion of an iterated integral. Iterated integral. So an integrated integral is simply the idea of do x in rows, and then do the y in columns. So what do we mean by this? If I draw out my rectangle again, like that, and now just like you would do if you were a hay farmer, is I'm going to partition my x. I'm going to partition all my x's like that. So I have a bunch of rows that represent different y levels, right? So this is, the y-axis right here, going up like that. And we're going to partition the x-axis like that. And then I'm going to take my tractor here. If I was going to think of this as a tractor, there's my tractor. That's my combine that I'm going to add up, grab all the hay, and it's going to go, and it's going to do the integral in the x direction. So it's going to do all these rows going this way. And every time it goes to the end of a row, it's going to deposit a big bale of hay, and it'll deposit another bale of hay, and another bale of hay. And every row of the x's, we're just going to deposit a row of hay on the edge of the field. Okay? And that's going to be all of the x. For every value of y, we're going to do an integral in x. And at the end of the day, after we've done the entire stretch of the field, we're going to then do our y in a column, and we're going to take all of our bales of hay and take them home and take them back to the barn. And that's how we're going to do it. So let's do it for a specific example. So here we're going to get a new piece of paper here. So I'm going to talk about the function z is equal to y times sine y of x. All right, so we'd like to do an integral of this. All right, so the integral we're going to do is now, we'll call it I. That's the value we're looking for. And it's going to be the integral over the rectangle of y sine yx dA. All right, and so the rectangle in question here is going to be, I'll write it out like this, it's going to be 0 to 1 in the x-axis, and it's going to be 0 to 4 pi in the y-axis, like that. All right, so let's look at what this looks like. So one thing we want to do is we like to, in this class, do a lot of plotting. We'd like to visualize as much as we can with graphics what's going on. So one way we can write this as an integrated integral is to actually write it as 4 pi. That's the y integral. And then we're going to write 0 to 1 being the x integral, y, sine of y times x. We'll put the dx here. I'll put a little parenthesis around that. And this is me doing my rows of x, of all the x variables, of all the x integrals, I should say. And there's the dy on the outside. And the idea is that we're going to do x integrals and keep y fixed. And then when we're done, after we've done all of those, we do the big integral then, so that's number 1. And then 2, we're going to do all the y integral. All right, so before we get started on this integral, what I'd like to do is actually is to plot what this surface looks like. All right, we want to see what this surface looks like on this rectangle. So let's do that. All right, so what I'm going to do is I'm going to open up a Matlab script here. I'm going to get out my. So the first thing I'd like to do is just go CLC, and that just clears my screen. So I'm going to press play on this. Sorry, we'll hold off on that for right now. But all that's going to do is zero out all of my work. All right, so what we're going to try now is to plot this thing. So what we need to do is define our x and our y. So first of all, we'll define our dx, and now I'm going to define it pretty coarse grain. So 0.1, that'll be my partition of the x-axis, and dy is going to be, we'll say it's 0.2. All right, and then we want to go and make our x and y vectors. And we're going to do it in a special way, and Matlab has a nice way of plotting three-dimensional things if you use this function called mesh grid. So it's going to create my x and y values. So mesh grid, then so I said I wanted to start at 0. I'm going to go forward by dx increments, and I'm going to end at 1. And now for the y-axis, now I'm going to start at 0. I'm going to go dy, and I'm going to end up at 4 times pi. All right, so that's nice. Now we have that. So now let's write down our function. Z is going to be y. We use the dot time symbol because we're multiplying vectors component-wise together, times sine y dot times x, and that's going to be my z-axis. So now we put it all together. I'm going to call up a figure 1, and I'm going to do a surface plot, which we call surf. And then we just go x, y, z. That looks good. And to make things look a little smoother, it's a little bit easier to see what's going on, I'm going to tell the plotting tool to say, this tells the plot, the surface plot, to not put grid lines on things. So I'm going to say shading interp. And that means that we're going to shade the surface interpolated so it won't have lines all over it. It'll just look like a nice colored thing. All right, so so let's try this out now. Let's give this a shot. All right, so there we go. All right, so here is my. I'm gonna make it bigger. So I'm going to use my rotate tool. I'm going to rotate that on, and that's what the surface looks like. All right, so here, this is the x-axis. It goes from 0 to 1, and here is the y-axis. It goes from 0 all the way to well, about 4 pi. Okay, so so it has a very strange shape. You can see that again, the function, right? The function is y times sine. So when y is equal to 0, i.e. when the y-axis goes all the way down over to here, that the z value should be 0, and you see it's just constant. But as y gets bigger and bigger and bigger, the amplitude, if you can think of this function here as sort of an amplitude, the y is an amplitude that's attached to this wave here. And y can also be considered sort of a frequency in terms of the x domain. So we can plot that there. We see that it starts, and first there's as x goes across here, you see there's one kind of wave, if you will, and it goes down. And then if you take a y value a little larger, there's a little bit faster frequency wave. It goes up and down, and those red regions are the regions of high elevation and low elevation. All right, that looks good. All right, so now let's actually integrate this thing. All right, so what I'm going to do is actually, so we said that the integral is essentially a double sum over all of our values. So what we're going to do is we have this z. If I actually write down what z is, if I just write it and I don't put a semicolon, it'll actually print out. And it makes this very giant matrix of numbers. So we want to add up all those numbers, right? And we want to add them up and we want to weight them by the correct thing. So I'm going to say dA is actually dx times dy. And I'm going to say that the integral then, I, is going to be the sum. It's going to be the double sum of z, and I'm going to multiply everything by dA. All right, so let's figure out what this is going to be then. I hit return. We see that the I value then is around 11.4. All right, so that's with a fairly crude grid, a very, very coarse-grained grid for our thing. So let's go back now and actually write down. Hold on. Where's my? There it is. Okay, let's actually write down and compute this integral by hand and see if we can get a better approximation. We can actually get the true value, not a better approximation, but the true value of this integral. So let's do it. So again, I said I was equal to. So what I'm going to do then is do this. I'm going to bring this down here, and I'm going to take that inner integral. What we're going to do then is keep y fixed, but do the x integral. So we see that we have this integral is 0 to 1, and we have a 0 to 4 pi on the outside, and then we have a y sine yx dx dy. I see this in here. I see this y on the inside. I also see a y on the outside, so it motivates me to do a u substitution. Yx, and what I want to do is go du dx. I'm taking the derivative with respect to dx there, and I should just get y, and that means if I see a du over y, that equals a dx. And so putting all that together, the outside integral stays the same, 4 pi, and the inner integral then becomes something else. It becomes, let's look at the thing. So if I put a 0 in here, I get a 0 out, but when I put a 1 in for x, I get a y out. All right, remember y is a fixed parameter in the x integral, and then that becomes sine u du. And then we put the dy out there. We haven't done anything with that integral. So what is the we know the antiderivative of this is going to be, of course, negative cosine of u. And then we're going to evaluate it at 0 and y. And then we're going to put that all around 0 to 4 pi dy. Finally, we can compute this all the way through. That becomes integral 0 to 4 pi, and we have to evaluate the difference of those two things, so that becomes cosine of 0 minus cosine of y dy. So cosine of 0, that's actually just 1. So the integral of a constant is, of course, just going to be y. We're going to evaluate that at 0 to 4 pi minus, so what's the antiderivative of cosine? Well, it's going to be sine y, and we're going to also evaluate it at 0 to 4 pi. So this one's going to go away because sine is 0 at both 4 pi and at 0, and that leads us to y. If we evaluate this, it's going to be 4 pi. All right, so what is the numerical value of 4 pi? All right, so well, let's write it down on our editor. So here is our approximate integral. So here's the actual value. It's going to be 4 times pi. All right, so let's see how good my approximation came up to be. All right, so the actual value is 12.5664. All right, so that's 4 pi to full accuracy. And obviously this is in the ballpark of correct, but not quite. So what we really want to do is crank down our partitions. Why don't we make these a little bit smaller, like that. So now we'll make them both 0.01. All right, so that makes the sum much longer, much more, there's more numbers to add up, but we should get better accuracy. All right, so now we're within 2 significant digits. We have I is equal to 12.49 as our approximation, and the actual value is 12.56. So we still need to get quite a bit more accurate, or quite a bit smaller meshes to get more significant digits. Right now we only have 2 significant digits, so why don't we just try going down another order of magnitude. Well, let's just go down half an order of magnitude. So let's try that. All right, so now we have 3 significant digits here between the actual value and the full value. So then we'll try going down a full order, another half order of magnitude, all the way to 0.001. So now we have a very, very long sum to compute. But now we get a significant accuracy to 4 significant digits. So yes, just doing a straight double sum will get the correct value. All right, so thank you very much.